what empty actually means.
Right. We just picture this void, total nothingness.
Exactly. But what if, like even in that absolute nothing, there's this constant buzz, this quantum weirdness happening that actually shapes our universe?
It sounds completely counterintuitive, doesn't it? Our everyday sense of things just breaks down at that scale.
It really does. We think vacuum, empty. End of story.
But quantum mechanics says, nope. It's more like this simmering pot of potential. Energy's never quite zero. Things are popping in and out.
In the blink of an eye. Okay, so that's our mission today for you listening in. We're drawing on some really cool explanations about quantum fluctuations, the uncertainty principle, the quantum vacuum, all that good stuff.
Yeah, the goal is to really get a handle on this. What are these fluctuations? Where do they happen? And crucially, how do they have these real effects?
Effects on everything, from tiny particles all the way up to, well, the whole cosmos. So let's start with that vacuum idea. Classical physics, for ages, said empty space is just empty.
Utterly empty. No energy. A blank slate.
But the quantum view,
Yeah.
totally different. You mentioned it sees the vacuum as the lowest energy state of quantum fields.
Exactly. Imagine the universe isn't just space, but it's filled with these invisible fields, like an electromagnetic field or one for electrons, everywhere, like an invisible ocean.
Okay, I think I can picture that. So these fields, even in a vacuum, they're not just dormant, they're humming along.
They're humming. And that brings us straight to Heisenberg's uncertainty principle.
Ah, yes. Which isn't just some math thing. It actually explains why empty space isn't really empty, right?
Precisely. One version of it, the energy time one, basically says you can't know both the energy of something and the exact time you measured it with perfect precision. There's a trade-off.
So IE times height has to be more than some tiny number.
Right, 6 divided by 2. What that means is if you look at incredibly short time intervals, the uncertainty in energy, theory, can be really quite large.
So, okay, for a vanishingly small moment, the universe kind of lets energy conservation slide a bit. The vacuum can sort of borrow energy.
As long as it pays it back super fast.
Yeah.
Yeah, that's a good way to put it.
Yeah.
And here's where it gets really wild. That borrowed energy.
You can become particles.
Yes, Einstein's E-5. That borrowed energy can pop into existence as mass, specifically a particle and its antiparticle pair. Think electron and positron.
And these are the virtual particles. Virtual meaning, like, not quite real, temporary.
Temporary is the key. Their whole existence is dictated by that uncertainty principle time limit. They appear, they exist for that fleeting moment allowed by the borrowed energy, and then poof, they have to annihilate each other.
And pay back the energy loaned to the vacuum.
Exactly. They can't just hang around like the particles that make up you or me. Physicists say they're off-shell.
Off-shell, meaning they don't have to follow all the usual rules.
Yeah, kind of. Real particles have strict relationships between energy, momentum, and mass. Virtual particles, because they exist so briefly, have a bit more flexibility. They don't strictly obey E equals PC plus MEC MERO. This off-shell nature is really important for how they mediate forces.
Okay, but even though they're so short-lived, you're saying they have real, measurable effects.
Absolutely. That's the mind-bending part.
All right, so this quantum flickering, this virtual particle soup,
Yeah.
it's not just happening way out in intergalactic space.
Mhm.
It's everywhere. In this room.
Everywhere. The fundamental fabric of space-time is doing this constantly, but it's also happening within quantum systems, too.
Like inside an atom.
Yeah. Think about an electron in its lowest energy state, its ground state, orbiting a nucleus. Even there, its position isn't perfectly fixed. It jitters. It fluctuates because of quantum uncertainty.
So it's a basic feature of the quantum world, this constant uncertainty and fluctuation.
Okay.
Now, this might still feel a bit theoretical, the ephemeral particles, energy loans.
Right. It sounds abstract.
But you said measurable effects.
Yeah.
Let's get into the proof. What's the evidence? First up, you mentioned the Casimir effect.
Ah, the Casimir effect. It's beautiful. Okay, picture this. You take two perfectly flat, neutral metal plates, put them in a vacuum really, really close together.
Right.
Now, all around these plates, virtual photons of all possible wavelengths are popping in and out of existence, right? Because of those vacuum fluctuations.
Makes sense. Photons are particles of light mediating the electromagnetic force.
Exactly. But between the plates, because they're so close, only virtual photons with wavelengths that fit neatly into that tiny gap can really exist. Think of it like fitting standing waves on a guitar string. Only certain lengths work.
Ah, so there are fewer allowed wavelengths, fewer possible virtual photons. between the plates compared to outside.
Precisely. And this difference creates a tiny imbalance. There's slightly more quantum pressure from the virtual photons outside pushing in than there is from the ones inside pushing out.
So the plates get pushed together by nothing, by the vacuum fluctuations.
Yes. An attractive force arises purely from the vacuum activity. It's incredibly small, but it's been measured experimentally multiple times, and the measurements match the theoretical predictions beautifully.
That is genuinely astonishing. A force from emptiness. Okay, what else? The Lamb shift. Something to do with hydrogen.
Yes, the Lamb shift. So basic quantum mechanics predicted that two specific energy levels in the hydrogen atom, they're called 2s0 and 2p0s, should have exactly the same energy. Degenerate, we say.
But measurements showed.
Measurements, incredibly precise ones, showed a tiny difference, a very small energy gap between them. This was a puzzle.
And the explanation involves, don't tell me, virtual particles.
You got it.
Yeah.
The electron in the hydrogen atom isn't just interacting with the proton, it's constantly interacting with the sea of virtual photons fluctuating in the vacuum all around it.
So these virtual photons are nudging the electron, affecting its energy just slightly.
That's the idea. They perturb its energy levels, splitting those two levels that should have been identical. Another direct consequence of vacuum fluctuations.
Incredible. And there's more, right? Something about magnetism.
The anomalous magnetic dipole moment. Okay. Particles, like electrons, have an intrinsic magnetic property, like a tiny bar magnet. Simple theories predict a certain value for how strong this magnet is.
Let me guess. Experiments showed it was slightly different. An anomaly.
Exactly. The measured value is just a tiny bit off from the simplest prediction.
And quantum fluctuations again.
You bet. The electron isn't alone. It's interacting with that cloud of virtual particles, virtual photons, even virtual electron-positron pairs flickering into existence around it.
So that cloud slightly changes the electron's magnetic properties.
Precisely. And quantum electrodynamics, QED, which is our theory of electromagnetism, including these fluctuations, predicts this anomaly with stunning accuracy, like to an incredible number of decimal places. It's one of the most precisely tested theories in all of physics.
Wow. Okay, so Casimir, Lamb shift, magnetic moment. That's pretty compelling evidence at the small scale. But you mentioned cosmology, too. How did these tiny fluctuations affect the whole universe?
This is maybe the most mind-blowing connection. Think back to the very, very early universe. Seconds, or even fractions of a second after the Big Bang, there was a period called cosmic inflation.
Right, when the universe expanded incredibly rapidly, like exponentially fast.
Exactly. Now, even before and during inflation, the universe wasn't perfectly smooth. There are these tiny quantum fluctuations happening everywhere, just like they do now. Little variations in energy density from place to place.
Okay, microscopic jitters.
Microscopic, yes. But then inflation happened. This enormous stretching of space took those tiny quantum scale fluctuations and blew them up to astronomical sizes.
Whoa, so the quantum jitters got stretched across the cosmos.
That's the prevailing theory. These stretched out fluctuations became tiny variations in the density and temperature of the early universe. Little patches that were slightly denser or slightly hotter than others.
And those acted as seeds.
Seeds for structure. Over billions of years, gravity took over. Those slightly denser regions had slightly more gravitational pull. They attracted more matter.
And eventually grew into galaxies and clusters of galaxies and the whole cosmic web we see today.
That's the picture. Without those initial quantum fluctuations, amplified by inflation, the universe would likely have stayed almost perfectly uniform. Smooth and featureless. No galaxies, no stars, no us.
So the largest structures we see originated from the smallest possible quantum uncertainties. That's profound.
It really is. And we can actually see the imprint of these primordial fluctuations in the cosmic microwave background radiation, the afterglow of the Big Bang, the temperature variations across the CMB sky map directly back to those initial quantum seeds.
Unbelievable. Okay, so let's try and summarize the big picture here. What are the main takeaways from all this?
Well, first, reality at its most fundamental level is fuzzy. It's probabilistic, it's dynamic, it's constantly fluctuating, even in supposedly empty space. Our classical intuition of a clockwork deterministic universe just doesn't hold up.
And it sets fundamental limits, like the uncertainty principle limiting how well we can know certain things simultaneously.
Right. It's also absolutely central to particle physics. Quantum field theory, our best framework for describing particles and forces, has fluctuations built into its very core. It's how we understand interactions.
And as we just discussed, it's crucial for cosmology seeding the structure of the universe.
Yeah. And if we look closer at the vacuum itself, It's not just empty potential. It has properties like Lorentz invariance. The laws of physics look the same regardless of your constant velocity.
Okay. And you mentioned zero-point energy before, the idea that the vacuum has a minimum energy level that isn't zero.
Exactly. Think of a simple quantum system, like a pendulum or a mass on a spring. Even in its lowest energy state, it can't be perfectly still because of the uncertainty principle. It always retains some minimum vibrational energy, the zero-point energy. Quantum fields are like infinite collections of these oscillators, and the vacuum is their collective ground state, possessing the zero-point energy.
But doesn't that lead to problems? If you add up all the zero-point energy from all possible fluctuations everywhere.
Yes. You hit on a big one. Naively, summing it up gives an infinite energy density for the vacuum, which is clearly nonsense.
So how do physicists deal with that?
Through a set of techniques called renormalization. It's mathematically quite involved, but the gist is that we figure out how to separate the infinite parts, which often cancel out or can be absorbed, into redefining physical constants. We measure experimentally, like mass or charge, from the finite, physically meaningful parts that predict things like the Casimir effect or the Lamb shift. Often, it's only energy differences that matter physically.
Okay, a mathematical toolkit to handle the infinities. But does this relate to dark energy? I feel like I've heard about vacuum energy in that context.
You have. This leads to arguably one of the biggest mysteries in physics today, the cosmological constant problem. When we try to estimate the vacuum energy density based on quantum field theory, even after renormalization tricks, the value we get is enormously larger, like 120 orders of magnitude larger than the observed energy density of dark energy that's causing the universe's expansion to accelerate.
120 orders of magnitude. That's not even close.
Not even in the same ballpark universe. It's a huge discrepancy, telling us we're missing something really fundamental about how gravity and quantum mechanics connect, or about the nature of the vacuum itself.
Wow. Okay. Any other weird vacuum ideas?
While some theories suggest there might be multiple possible vacuum states, like different possible lowest energy configurations for the universe's fields. Perhaps the early universe cooled and settled into the specific vacuum state we inhabit today. This is tied into ideas about symmetry breaking in particle physics.
Fascinating stuff. Let's circle back to the virtual particles themselves. You said they were off-shell. How does that relate to them carrying forces?
Right. So being off-shell means they don't strictly follow the energy-momentum-mass relation of real particles, Emping TC plus MCC. This freedom is linked to their short lifespan via the uncertainty principle. It allows them to exist virtually to mediate forces.
So when two electrons repel each other,
they're exchanging virtual photons. Those photons are the messengers carrying the electromagnetic force. Because photons are massless, the force can have an infinite range.
and for other forces.
Same idea. The strong nuclear force holding quarks together inside protons and neutrons is mediated by virtual gluons. The weak nuclear force, responsible for certain types of radioactive decay, is carried by massive virtual W and Z bosons.
And because the W and Z are massive.
Exactly. The uncertainty principle links mass, energy to range. Heavier virtual particles can only be borrowed for shorter times and travel shorter distances, which is why the weak force has such a tiny range, confined within atomic nuclei.
So the properties of the virtual force carriers dictate the range of the force. That makes sense.
Yeah. And physicists have these great visual aids called Feynman diagrams. They draw little diagrams showing particles interacting by exchanging these virtual particles. It's a powerful tool for calculation.
But still, we never see a virtual particle directly.
Correct. Their existence is inferred entirely from the effects they produce, the forces, the energy shifts, the magnetic moments. Some physicists even prefer to avoid the term virtual particle and just talk about interactions between the quantum fields themselves. It's a bit of a philosophical preference sometimes.
Okay. And are fluctuations only in the vacuum or around real particles too?
They're definitely around real particles. A real electron, say, isn't just a bare point charge. It's surrounded by this constantly fizzing cloud of virtual particles interacting with it.
And this cloud affects the electron.
It does. It effectively screens the electron's bare charge, so the charge we measure from a distance is slightly different from what it would be up close. This is part of what renormalization handles, relating the theoretical bare parameters to the actual physical dressed parameters we observe.
Dressed by the virtual particle cloud. Got it. And how is this different from, say, thermal fluctuations, like heat jiggling things around?
Good question. Thermal fluctuations are driven by temperature, by heat energy. They become more important as things get hotter. Quantum fluctuations are inherent to the quantum nature of reality itself, existing even at absolute zero temperature where thermal fluctuations would cease. They're a fundamentally different beast.
Okay, and one last really dramatic example. Hawking radiation. Black holes getting involved.
Near the event horizon of a black hole, the gravitational field is incredibly intense. So intense it can affect these quantum fluctuations. Imagine a virtual particle-antiparticle pair pops into existence right at the edge.
Uh-oh.
It's possible for one particle to fall into the black hole while its partner escapes out into space.
But didn't they borrow energy from the vacuum? If one escapes, how is the energy paid back?
The particle that falls in effectively has negative energy relative to an observer far away because of the weirdness of space-time near the horizon. So when it falls in, it reduces the black hole's mass energy. The escaping particle carries positive energy away.
So the black hole evaporates. Slow.
Very, very slowly for astrophysical black holes, but yes. It radiates energy as if it were hot, due purely to these quantum effects at its horizon. It's a stunning prediction linking quantum mechanics, gravity, and thermodynamics.
Mind blown. Okay, and just to really nail down the uncertainty principle one last time, it's not just that our measurement tools are clumsy.
Absolutely not. It's deeper than that. It's a fundamental property of quantum systems. An electron does not possess a definite position and a definite momentum at the same time. The fuzziness is inherent.
It's linked to wave-particle duality, right?
Exactly. If you want to pinpoint a particle's position, make its wave packet very small, you need to combine waves of many different wavelengths, which means its momentum, related to wavelengths, becomes very uncertain, and vice versa. Same logic applies to energy and time, frequency, and duration.
Okay, so wrapping this all up, the big takeaway is that even the emptiest void isn't empty. It's this seething, dynamic place, thanks to quantum mechanics.
A stage for constant fleeting activity, governed by the uncertainty principle, filled with virtual particles popping in and out.
And the proof isn't just theoretical math. It's the Casimir force between plates, the Lamb shift in atoms, the precise magnetic properties of particles.
And even the large-scale structure of the entire cosmos, seeded by these quantum jitters in the infant universe.
It really makes you rethink reality. This underlying fuzziness, this uncertainty, somehow gives rise to the stable, structured universe we see. So here's something for you, our listener, to chew on. If the foundation of everything is probabilistic and jittery, what does that say about the solid, predictable world we experience day to day? Is it all just a macroscopic average? And what does it mean that our entire universe, in a way, grew out of quantum noise?
Deep questions. Definitely something to ponder.
Indeed. Well, that's all the time we have for this deep dive. Until next time, keep questioning.